Yeah, thanks for coming to this talk. It's about automating big data platform with Jenkins. And it's classified as being a non-technical talk. I would say it's like a less technical talk. There is some slides with code, but it's just for illustration. I'm here to talk about the past, present, and future of the big data platform we built, and the role Jenkins plays in that in serving the big data elephant. About me, I'm Kieft. I'm manager for all common components within Sanoma, and one of those components is the big data platform. And Sanoma is a publishing company. We publish about 100 consumer magazines and the 2 largest newspapers in Finland. And we have like 5 television stations, both in the Netherlands and Finland, and about 200 websites, under which like the largest news site in the Netherlands, largest portal, largest price comparison, and we have about 100 mobile applications. And these are generating like a lot of data. And in the past, we ran all this infrastructure and did all the analyses on like the systems that provided the data. Because already, back in the day, the data from the web analytics system and the advertising systems were too big to be able to handle in a traditional BI system. So we got like the high-level aggregates, combined them in Excel, and then used that for reporting. But somewhere in 2010, a use case came along for starting to combine this data. And we've been toying around with this thing that's called Hadoop. In 2010, also a simpler way of accessing that data came available, which was Hive, which is like a SQL layer on top of Hadoop. So we started with this project to combine the data from those various sources. And to give you a bit of an introduction about big data. By the way, who's familiar with big data and Hadoop? Okay, that's good I put in these slides, because yesterday at the drinks I was talking to a few people, and yeah, they pointed out, well, maybe do some sort of introduction, because maybe not everyone is familiar. And what we wanted from the data, we had a few particular use cases we wanted to solve, but we knew that there was in the data a lot more of value, but we just didn't know how to extract that yet. So we really bought into this idea. With in science, one man's noise is the other man's signal. So what some people consider to be garbage in the data, other people can extract value out of. And maybe not today, but maybe in 2 months' time, they think, hey, this is brilliant, this is in the data, we can leverage that. So with a traditional system, the way it goes, you get all this data, you refine it, and you put it in your operational data marts. So see it as bottled water. The rest goes to tape, but usually it goes to waste. It's not being used at all. With big data, you capture all the data you collect, and you store it in what's called like a data lake. And from this data lake, you can get these refined bottles of water. But it also allows you to go back to this lake with your bucket, take a scoop, and take that home for further analysis. And maybe feel like another more traditional data warehouse out of that. So when starts data becoming big data? It's a bit of a marketing slide, or at least it's used a lot in selling you big data solutions. But there's like the 3 V's. It's about volume, it's about variety, and it's about velocity. Where volume being like the sheer amount of data that you have to process or to get access to. The variety is both the number of sources, but also like the various formats of the data, being in documents or images or video or like XML files. And velocity is like the rate at which the data comes in. So how fast you have to process the data to be able to capture the insights from it. And usually it's not a single thing of these fees that make your problem, big data problem. It's usually like a combination. Because also for Sanoma, our volumes, wow, it's, especially I think for American market, it's like not that big. Variety, we have quite a lot of sources, but like the formats are pretty strict. The velocity, that is a thing for us because we want to provide these metrics in real time, do like user recommendations in real time. So we felt that like the combination of these made really a big data solution right for us. And it being a marketing slide nowadays, there's much more V's that have been added. And what's like the definition? It's like, this is the one we use. It's like structured and unstructured data which contain valuable information that cannot be processed by a traditional system, or at least against like acceptable cost and time. Because if you have money to spare, you can just buy a really big Oracle or IBM or Teradata appliance and dump all your data in, and your problem can be solved. But if you're working with, as we do, with like a lot of data, but in itself, per row of data, not really valuable, it usually makes it really hard to justify the cost for such a big appliance. And then about the variety, we don't have a lot of relational input data. We do have a lot of like semi-structured data, so being log files. And we have very little of like unstructured data. We have some of our content that we do analyze on our big data platform, but the majority for our sources is like semi-structured. Then the biggest difference between using a relational database system and a big data system is the difference on when to apply a schema. With a relational database system, you use schema on write. So when you insert the data, it's inserted using a certain schema. You define all the fields up front, the data is mapped to those fields and stored in a binary representation of that, and it's also retrieved in that way. With big data, it usually works different. You just put on the data in the format it originates in, and then you map the schema on top of that when you read it. Which gives you a lot more flexibility to evolve that schema over time. And like we said, maybe there's like some of the fields in the log that you don't initially expose because you don't see any value, but over time you can still capture the data by changing the schema, putting those additional fields in and leveraging those. And big data is about the difference between scale up and scale out. Whereas like these appliances or your relational database system is usually like a server and storage, usually on a SAN device or a network attached storage. And when your data volumes grow or you need more performance, you scale the solution. You just buy a bigger server, you just buy bigger SAN. But it becomes much more expensive quickly. Whereas with Hadoop, you start with one server with local storage. You add like another one, you add like another one. And instead of like growing one server, you grow the number of servers with keeping like the price of the servers down, or at least they're like what's called commodity hardware. We're not using desktop computers, but we just buy the most cost-effective Dell machines that we can find. So to harness that all that power, Hadoop is created, and that's like one of the de facto platforms associated with big data. And Hadoop came out of two papers that originally have been written by Google, the GFS paper and the MapReduce paper. GFS describing their way of the Google file system, of their distributed file system for building their web indexes. And MapReduce described an algorithm, functional programming using the map and the reduce, or the map and the fold operation for processing data. And being it functional, it's much easier to distribute. Some guys at Yahoo implemented that, made it open source, and that's what started the big data movement, if you want to call it like that. And over the years, a lot more programming ways have been added. So mainly going to talk today about Hadoop, which is like the core, being the distributed file system and the distributed processing, and Hive being like a SQL layer on top of Hadoop, so you can just use SQL to query your data. And when we set out to build this, we felt that not only have to scale this technically, but also organizationally. We needed to provide a way for everyone in the organization to leverage like the data that's on Hadoop. So we needed to introduce some level of self-service. So not everyone had to come to us to build the solution. But yeah, that required some more thinking, and yeah, being from Amsterdam, this is also what we consider self-service. So if you look at like the flow of data from the source to the insight, we started off with looking at like the last bit of this chain, and really opening up the way that the business analysts could use the data for building their reports and getting their insights. And we would take care of the first bit. So everything is great. We started out building this. We selected the tool for it. It's ClickView. It's like in-memory analytics. Then our data and data processing on Hadoop with Hive for like easy access to that data. And all we needed was like something to glue this together. And typically what you do with like a BI project is introduce an ETL tool, which stands for like extract, transform, load. Back then there were like 2 in the market that had connectors to Hadoop, so we were able to interact with Hadoop. We picked one of them, and it's like a graphical, like 4th generation language, which allows you to drag and drop certain processes and define that. And initially, well, that works, like the initial flow, gets the data on the cluster. Sorry. But when you start growing this, the flows start to get more complex, they're harder to debug, and the biggest problem, because we're working with big data, the performance is important, because like within 24 hours you have to do the processing for 24 hours of data, otherwise like the next day you can't keep up. And then you have to like parallelize some of the work so that it can run or can come in simultaneously. So that then your job starts looking like this. And you can imagine that now adding like the single field in all of these operations is like a hell of a job. So what you start doing, you start introducing some shell scripts to do the heavy lifting for you, taking away like all of the power of the ETL tool. So this part of the project failed dramatically. We had this really interesting components like Hadoop and ClickView, which provided a lot of value in itself, but like the integrations and working with the ETL tool didn't fit our use case. It didn't scale technically, it didn't scale organizationally, and we needed a slightly different mindset. I think we approached it too much as being like a BI project instead of being a development project. So we had to do a reset because all of these sources kept changing. And resetting meant that we also needed to rethink like the organizational scalability. And then we met this guy. This guy is Russell Journey. He wrote a book about agile data. And what he said was that you should make the entire stack self-service. So not only the last bit of doing the reporting, but you should open up the entire system to everyone that wants to use it. We found that initially a bit challenging, but we bought into the idea of opening much more to the stack and gradually moving forward in the way we exposed the data. But the tools we had didn't fit that, or at least the ETL tool we had didn't fit that. So we needed new glue. And then looking at the capabilities we need from this ETL tool, we need like processing, we need like scheduling, we need like data quality, data lineage, versioning, and annotation. What can provide these things? So we looked at a few options. We used a commercially supported open source product initially. We looked at using some commercial ETL tools. And we looked at some options from like the big data community, which we felt were not mature enough. Then we did a spike. We tried like 3 options and like benchmarked them against each other, how fast it was to integrate. And from that came that this was the fastest to implement. It was like a bash script reading in the files from a FTP location and putting them on the big data cluster and then doing the processing there. But there was a slight problem here. This is a loop for the non-technical people, and iterating this loop 10,000 times takes a lot of time, and that's due to the 3 Hadoop commandos that are there at the bottom. They all take like at least a half a second to start up. So then iterating this will take too long. So we looked at an alternative, and we found also a scripting language, but running straight on the JVM, so reducing the startup time and be able to execute much faster. It looks like Python, but it runs on the JVM. So this is Jython. It gives you like all the powers of a scripting language and the accessibility of Java and interacting with the platform. So that solved like the processing part. But now still we needed something for scheduling. And there we already had Jenkins in place because we were building like some of the jobs which are in Java with Jenkins. And Jenkins already has like this scheduling, it has this monitoring, it emails you when something fails. It has this nice dashboard we can put on our monitoring wall. It has really nice integration with the versioning control. And this was really a tool for developers. And we can also open this up to like other teams using to get their job scheduled on the platform. So this was really a natural choice for us, moving this to Jenkins. So then looking at those capabilities, for processing we have Bash and Jython. For scheduling we use Jenkins, versioning our code repository Mercurial, and for annotation we're commenting the code instead of printing out and highlighting the steps. So what do we use for processes? We try to make these independent steps, moving the data one stage to the next. And all these steps have a central role for Jenkins, because Jenkins is kicking off like all these separate steps. So this is like the extract, getting the data from a source system, usually FTP or API. It loads the data, puts it straight on Hadoop. And this is what helps like the scalability, because this is as fast as it gets. And like the next step, processing the data is happening on Hadoop. And there you really have the power of the cluster and being able to run it in parallel. So now your ETL tool or Jenkins is not a bottleneck anymore. It just kicks off the job, have it run on the big data cluster. And like the last step, Jenkins triggers the load to ClickView to expose the data to the dashboard users. Sorry? Yeah, it's okay. Yeah.
Jenkins is just scheduling the job, right?
Yeah.
But what is the scripting language is Jenkins?
Yeah.
So Jenkins is taking the raw data and putting it in Hadoop?
Yeah.
That's how it works?
Yeah.
So once it's in Hadoop, then what do you use to process the data?
Okay. Yeah, so the question was about loading the script. So what's the script being used in from Jenkins? That's indeed it's Jython. So Jython code gets the data from the source and puts it on the cluster. Then on Hadoop, you have various ways of processing that data. A bit dependent on the complexity. We use either MapReduce code written in Java. That's yeah, you like implement a map and a reduce function, or like various steps of that. There are also like higher level frameworks that make it easier to develop. That's like cascading, which gives you some higher level operators, which still boils down to MapReduce code. Then there's also a Scala wrapper on top of that, which is called scalding. We use, mainly our data scientists use that. So that's for jobs with a higher complexity. For like the simpler jobs, you can use Hadoop streaming, which then can still use Python or Bash or whatever. And when it's like really simple, you can immediately use Hive, which is like the SQL language, to use the processing. So if it's already like a CSV format, you can just put an external table from Hive on top of that and just use SQL insert into to move it and process it. Does that answer the question?
So what you're saying is, unlike RDBMS, where SQL is the only interface, right? To interact with RDBMS, Hadoop has multiple. So you would interact with Hive, you would interact with Java.
Yeah.
You would interact with different frameworks on that data.
Yeah. The question was if with RDBMS, SQL is the only way to interact, but with Hadoop you have like multiple ways of processing the data. Either like with MapReduce code or with streaming, or there's also Pig, which is like a simple scripting language on top of Hadoop, or Hive, which is then like SQL. So then what levels of self-service do we now have? So like the initial step, so like the extract, that's done with Jython, and that brings like the raw data in its native form onto Hadoop. That's what we expose to the data scientists. They write their jobs in cascading or in scalding, and they also execute that using Jenkins. So they schedule their jobs using Jenkins. And then we have the business analysts. They use like a more refined form of the data, where we create like normalized table names, normalized fields. But this is still not a modeled data warehouse, what you would typically have like in a star schema or in a data mart. That is happening by some of the other teams. One sec. And they create these data marts in like SAS or in business objects. So what do we use for like providing this self-service? One of those tools is U, which is the Hadoop user experience, which user interface on top of Hadoop, exposing like a lot of these functionalities, and mainly exposing like Hive. So users have an interactive way of typing like SQL and querying the data. Other tools like ClickView, already mentioned. The other one, more for like data science, is like our studio, which enables the data scientists to predictive analysis, really training a classification model or doing clustering, and then using that into some of the real-time systems. And Jenkins for scheduling everything. And with scheduling, we really find it practical to use the hashing scheduling, which tells your jobs to run in a certain time. So you define it should run in a certain hour, but you don't really care at what point in that in that hour. Giving a really nice way of distributing the load on the Jenkins server. The other thing we use from Jenkins, sorry, another thing we use from Jenkins are these parameterized builds, which allows users to just enter a few parameters and then run a build. So they can request like their custom report asking for a certain date range, or asking for a certain customer, or a certain website. So they just plug in the numbers, hit the build button, and then that job is ran with those parameters. We initially had really high hopes for this because we felt this is like a really nice way for users to interact. But currently it's not used as much as we thought. And that's mainly because we introduced like this other way of interacting from ClickView directly, where users define a query, and then ClickView triggers the Jenkins API. The job is loaded from ClickView. It's being executed on the cluster, and then the data is being exported. It is somewhat of a workaround, but it's mainly because of this performs much better than pulling the data from ClickView from Hadoop into ClickView. It's more performant to push it for some reason. And this is where we also use like the throttle concurrent build plugin from Hadoop, from Jenkins to lessen the load on the cluster. Like the main plugins we use in Jenkins is like the mailer for sending out the output, the LDAP connectivity for getting the access to the users and to the data scientists, in combination with the matrix authorization strategy, which gives you the flexibility to assign the roles to the projects, and obviously the Mercurial and the Git plugins, and the green balls. So how does this look together? We have like the sources. We have Jenkins as a central component with Jython, getting all the data from the sources onto Hadoop, scheduling the scheduled exports, the scheduled loads to ClickView, and we have Hive and U for more of the exploratory work. And there's an option to export that directly to ClickView or directly to our server. We're moving more and more towards like real time. We have our own logging infrastructure implementing like all the sites for getting the events, and then driving like recommendations. We use Kafka and Storm for that, and that's like added at the bottom. So the nice thing is that all the data we capture goes to Hadoop, so we can always do a replay of the data we collected, and it's then fed to like the real-time processes for doing like the recommendations. And this is what nowadays called like a Lambda architecture. And then the models that the data scientists build in R can be then exported and executed in real time for the recommendations or like classification. So what's our current state? Our current state is that we expose like all the light blue as really being self-service. The first parts can be used if developers want to extract their own source. They have access to Jenkins, they have access to the code repository. They can write it themselves. It rarely happens. That's usually what we do. But from there onwards, people are doing it themselves quite often. So we now have Jenkins and Jython, Kafka and Storm introduced recently. And in the beginning of this year, we moved to Yarn, which is allows for more processing paradigms on top of Hadoop instead of just doing MapReduce. So what are the use cases we do, or what are people doing with our platform? Mainly, it's like combining the data sources, so combining web analytics with our behavioral targeting system, with our advertising system. We're also doing A/B testing and analyzing the results that come from that. We also buy traffic for some of our sites. We have to optimize on the ROI of that. We provide like an ad auction, so customers can buy or can bid on ad space that we serve. For that, we do some price optimizations. We do ad targeting, so that's classifying users, saying, hey, this person is interested in cars. We'll show them car ads. And we do various recommendations and also some search optimizations. So still our main use case is for reporting, and it's increasingly shifting to data science. They're also like further down in the stack. It's like the common Sanoma big data platform used in the two countries. We have like 250 daily dashboard users and 40 analysts that really work on Hadoop itself and in Jenkins for these plus source systems, and then 125 different sources, which results in like 400 tables in Hive. The core team is actually pretty small. There's one product owner and 3 developers. They provide like the platform, Jenkins, and they get like the sources on the platform. And they support like the data scientists, the business analysts, and there's a guy supporting ClickView, so architectural support. Current platform is 55 nodes, 650 terabytes of proficient storage, and we run about 3,000 jobs a day, and some information about the nodes. So what's next for us? We have some challenges, and one of them is security, because we feel security is always an issue. You should also always be on your toes and really look in how you can improve that. And Hadoop especially is a harder to protect piece of infrastructure than maybe like a website. The infrastructure we're currently running on-premise, or at least in like co-location, owning our own hardware. We've done that since the beginning, and that mainly has to do with like the price point. Public cloud is really nice, gives you a lot of flexibility, but comes at like higher cost. So running the same infrastructure at like Amazon would be like 2 times as expensive. So we're really trying to balance what we do in our own infrastructure and what we do in public cloud. We want to improve like the integrations, and we want to improve some of the Jenkins stuff, because for us Jenkins is still a single point of failure. We have some issues with like big code repositories, and that's because like those 3,000 jobs that we run originate from like, I'd say 500 jobs in Jenkins, which almost all check out like the same code repository. We had once someone that by accident checked in some test data, which turned out to be, I think, 2 or 3 gigabytes, but then having that checked out 500 times caused some issues. The way Jenkins upgrades is not really convenient for us, because it has to shut down. That in combination with like the long-running jobs is not so practical, because there's jobs that run for like 14 hours, and when you have to do like an upgrade, yeah, you either have to break off that job or wait until that job is finally completed and have like the restart, which can then be in the middle of the night. And then, yeah, because of the single point of failure, we want to increase the redundancy, maybe introduce some more build slaves. So, to wrap up everything, the main takeaways is Hadoop and big data open a lot of opportunities for your company. There's a lot of data you can more easily access and use for driving improvements in your product or new insights. You can easily capture more data and start using it later, also in like an iterative way. You can get started really quickly with like a simple use case, but start capturing a lot more data, and then in time start expanding on the usage. Hadoop requires developers, and developers like using development tools, and like Jenkins is a really good match for that. And Jenkins might not be the best solution, and it's not a real natural fit for big data, but it's a good enough solution, at least for us, and it solves the problem well enough for now. Like I said, you can start small with big data. So that's like my main takeaways. Are there any questions? Sorry, I have to come over.
Why do we need Jenkins? Why not we use like Control M or something like that? Schedule.
Like what?
Control M or Autosys. Job schedulers, cron.
Yeah, oh yeah, you can obviously use cron, but that doesn't have any dependency management, that doesn't have like the monitoring, that doesn't have like the nice reporting wall. And yeah, it requires your developers to go and edit like the cron file. This gives you like a nice web interface. Users can enter their jobs there. So yeah, I think this was a more friendly. One of the things cron does not have is the hash scheduling, which is like really important, because if you're running like the 500 jobs and some of them you run hourly, you really want to spread out that load and not being there manually picking, like you can run at 5 minutes past the hour, you can run 10 minutes past the hour. The H scheduling takes care of that for you.
But you have 500 jobs. They're all interdependent of each other, right? So you have predecessors and descendants.
The question is, what are the dependencies? We really try to limit the dependencies, because if you really design the jobs to be independent and really just put the data to like the next stage, you can have all the jobs independently, like monitoring their input directory, and just process what data is there, which gives you a lot more options to do reruns of your data. Whereas if you really make a huge dependency graph of that, it becomes much harder to manage those. So we do use that, but we try to limit it as much as possible and really make them like atomic steps.
Jenkins give you a good view of that, where you can see your interdependencies?
You can use the dependency graph plugin. That's
I was wondering, you mentioned that if Jenkins was good enough, and I was wondering the deficiencies that kind of take it, up to only good enough. I mean, you just gave some explanations that almost sound like, well, it does sound like it's good enough, or almost, much more than some of the alternatives. So I'm wondering, what's that gap for you?
The gap is in the redundancy. So being at a single point of failure, yeah, maybe you can go support it and go for like the master-master setup. But we have not looked into that that enough. I think some of the dependencies are in, of the shortcomings are in like the updates, and having to restart with like all the updates and not having like a separation between like the coordinator role and like the executors in some sense, because that would be like really convenient to just have these build slaves run autonomously and just report back on like the job stage, which allows you to just reboot the master or the scheduling service. Some other shortcomings, let me see what was there. Yeah, so the big repositories, now for every job we're like checking out the full repository, and it has some minimal framework, so it needs like the entire thing. Yeah, maybe having an option to refer like a already checked out repository would be an improvement. Yeah, I think that's moving like the dependencies to like a data level instead of like a job level. That could be interesting. That's also like what some of the other companies are doing. So like LinkedIn is building Azkaban to solve this problem. And Spotify built Luigi, which also like contributions from some other companies. And they're mainly focused on like these data dependencies and building like the dependency graph for those processes. And yeah, we really try to build the autonomous steps. So we have less need for that. Does that answer the question?
Thank you.
Other questions? Okay, and thank you for your time. And the slides from the organization, you can leave your feedback somewhere in the app. Okay, thanks.